So all of these things are related with the acids and the bases because for every acid, it has a conjugate base. Every base has a conjugate acid. And so if you have a stronger acid, the stronger the acid, the weaker its conjugate base. And the stronger the base, the weaker its conjugate acid. And this becomes very important in doing these problems. So here's a little table that emphasizes that fact. So we talk about a strong acid. Most people are familiar with HCl, hydrochloric acid. So it's a very strong acid. And its conjugate base, Cl minus, is not really a base. It's completely ineffectual as being a base. It doesn't really do anything at all. A strong acid really drives you all the way to hydronium ion concentrations. It doesn't go back the other way. It's not really equilibrium. It's just going to completion there. So the conjugate is really, really weak, basically not a base at all. Then we get into this middle range, and here things that are moderately weak or very weak acids also have their conjugates in the weak range. But if you get to something that is a very strong base down here, its conjugate is going to be also ineffective as an acid. So if something is very strong, its conjugate is pretty much non-existent in those properties. But when you have weak, then you can start talking about buffers, which we're going to get into later in today's class. OK, so let's prove that, in fact, it has to be true that there's a relationship between the conjugate acid and its conjugate base, or conjugate base and its conjugate acid, that they both can't be strong. One has to be, you have to be weak, strong, or ineffectual. All right, so let's look at the first one up here. So first, let's look at what is this acting as? What is NH3 acting as, an acid or a base in this equation? So it's acting as a base, and that means water is acting as an acid. The water gives up a proton or hydrogen ion to the NH3, forming the conjugate acid of that base, and then the conjugate base is the hydroxide ion. All right, so now let's write term for K. And so we're talking about a base in water, so we're talking about Kb. So Kb is going to equal what? What do I put up here? Tell me one thing to put up there. Yeah. I'm missing my plus there. OK, NH4 plus and hydroxide ion over NH3. OK, so we don't have water in there. All right, so let's look at the next reaction. I wasn't fond of pluses up here. OK, let's go up. That's pretty much good enough. All right, so what is NH4 plus acting as? It's acting as an acid here. So it's giving up its proton or hydrogen ion to the water, which is going to act as a base and accept that hydrogen atom. And when this gives up its hydrogen ion or proton, it forms its conjugate base. And the water's conjugate here is an acid, hydronium ion. So we have our conjugate acid-base pairs here. So now am I talking about a Ka or a Kb? I'm talking about a Ka. So I'm talking about an acid in water. And we know this is an acid in water if we look at what's happening over here. So we have an acid in water. And so we'll put our concentration of hydronium ions and NH3 over NH4 plus. So now we have Kas and Kbs written for the conjugates, the conjugate acid of NH3 and NH3 itself.